Okay, welcome everybody. Just have to check. Am I hearable right now? Yeah. Okay, great. So my presentation will be about explainable AI with Python. First, I'm going to introduce myself for a bit. So I have a background in artificial intelligence. I studied artificial intelligence in Nijmegen. I did a Bachelor of Science, then a Master of Science, and then I joined the Netherlands Forensic Institute as a software engineer and a data scientist. And I'm currently employed at the Rijksdienstlegergilde. And via the Rijksdienstlegergilde, I'm placed at the municipality of The Hague, which I've just started this week, actually. So yeah, I think that's enough about me. Let's go to the agenda of today. First, I'm going to quickly mention what explainability is, what I think it means, and I'm going to quickly show some machine learning models. I think most of them are familiar for you, but just sorry, yeah. And then I'm going to explain some explainability methods, the broad categories of methods, which methods fall into, and then some methods, some explainability methods, and then I'll end up with a wrap-up and a conclusion of my talk. So explainability, I think when you build a machine learning model, you will focus on accuracy and performance because you want to build the best model. But I think recent events have shown that it is not always that the most accurate model is the best model, but also a model that can be explained, and that can also questions of users. For example, if you're getting a discount in a web shop, you may want to know why you are getting that discount and your neighbor isn't. Your neighbor might want to know what he can do to get the discount as well. If you are driving in a self-driving car, you might want to know what the priority of the car is. Is it your safety or the safety of as many people as possible? So will it drive over pedestrians to save you, or what will it do? And the reason why we want this explainability is mainly, first of all, because sometimes we just have to, because of the GDPR. But also it's very useful to spot discrimination and fairness and non-fairness, so we can solve that. And it is useful for the users or the citizens to gain trust in the models. And well, if the models are transparent, we want everyone to, we don't want the models to be some kind of magic for them, but we want them to understand what's going on. And that happens by answering these simple questions above. So I'm quickly going to show some machine learning models. I'm not going into detail, but the point is that some models are explainable by nature, interpretable by nature, and some models aren't. Yeah, so this is it. So for example, regression models are really interpretable by nature. You can look at the coefficients, and you can see what the model does. Same for decision trees. You can really look at the tree and see if a certain variable takes a certain value, you can see what that means for the prediction. And then there are also non-interpretable methods, which are, for example, neural networks and random forests. So an example of linear regression, we can see that if the x variable rises, is higher, then the prediction is higher as well. So for decision tree, we can literally look at the tree and see what it means to be female for your chances or the predicted chances of survival in the Titanic disaster. But for neural networks, it's a different story, because all these lines are multiplications, and there are also biases added at every node. So we can't interpret the relation between the inputs and outputs anymore easily. The same thing for random forest. We can interpret every individual decision tree, but we can't interpret this entire collective of trees. Okay, so now the main part of this talk is going to be the explanation of 3 different explainability methods. And the first one is, okay, the categories of explainability methods, which is on 2 axes actually. You'll either have the model agnostic or the model specific explainability methods. And the model agnostic method works for any model. It most of the time is a kind of a wrapper around that model. And the model specific explainability methods use the structure of that specific model to explain the model itself. So we can see a picture of a decision tree as a model specific global explanation of that decision tree. Because global means that you explain the entire model, and for a local explanation, we just explain one instance or one prediction. We explain why that prediction is the way it is. So for this first example, I've trained an uninterpretable model. It's not really relevant which one. It's a random forest to predict the median house value from a set of other variables. So the age of the house, the number of occupants, the geographical location of the house. And we can see that the ground truth is 1.65, and the algorithm thinks or the model thinks it's 0.88, which is not even close. So we want to see why there is so much difference between the two. So the first method I'm going to explain is a breakdown plot. And what that does is it describes the change in average prediction on the training set after fixing each variable to the value that it has on the instance we want to have explained. So I think it's best if I just show with an example. So this is the training set. So the average prediction in the training set is about 2. So we take that as our intercept, the first value in our breakdown plot. And then we're going to fix latitude to 39.44, which is the latitude value of the instance we want to have explained. And then we can see that the average prediction drops quite a bit, by a half. So that's what we're going to write down. We're going to write down minus a half for latitude equals 39.44. We do the same for longitude. We can see that the average prediction rises a bit, and we write it down like this. So essentially we end up with a lot of number of copies of our instance. And the average prediction, of course, is 0.88 because that was the prediction of that test sample. So this is what our breakdown plot looks like in the end. So we can see that latitude and median income have quite a big effect on the prediction. And this is very easy to code in Python by using the Dalig package. The Dalig package is a great package for many explainability methods. I'm also going to, my next method is also in Dalig. Oh, I'm not using the microphone, I think. And so basically we build an explainer object, and then we build we call the predict paths method on that object with the type breakdown. And we also specify the order of variables in which we want the variables to be fixed to the values they have in the test sample. And then we plot it. We can also change the order of the variables around. And then we will have, for example, longitude first and then latitude. And that brings quite a difference in the breakdown plot, actually, because for the first, the contribution of latitude is minus a half, and for the second, the contribution of latitude is minus 1, which is way bigger. So that's quite problematic for breakdown plots, that we do not really get one value that quantifies the contribution of that variable to the prediction. So to illustrate this, I sampled 50 different orderings. I created breakdown plots for each ordering, and I stored the contributions in a dictionary and plotted the dictionary. So this dictionary in the end has the keys, with the keys being the values, the variables, and the values being 50 contribution values coming from all of these breakdown plots. And then we can see that, for example, latitude, the contribution value of latitude is somewhere between minus a half and minus 1.5. For some, the variability is a bit smaller, but it's not useful that there is such a great range of possibilities. So I think the pros are that it's quite understandable. We can really see what's going on. It is also intuitive because it really makes sense to fix a certain variable to a value and see what it on average does in a training set. And it's quite compact. If you have just a few variables, it's a nice little plot. The negative parts of this is misleading for interactions because at least the way I showed it, you can also fix multiple variables in the same time. But if you fix one at a time, we do not see the interaction effect of variables unless you fix them after each other, but then you have to calculate that for yourself. And the order matters. That's the biggest drawback of this method. So a solution for this order problem is Shapley values. And with Shapley values, we calculate the contribution of each variable, or the value of each variable, to the prediction. This originates from game theory, and there it means that we try to quantify the contribution of one player to a cooperative game. And what we're going to do is we're going to add a value of the test instance per variable to the coalition of other variables. And we compare this with a random value for this variable we want to quantify the contribution of. So maybe this will also become a bit clearer with an example. So for example, if we would have a simple model with just 3 predictive variables from the previous set, so the number of occupants of a house, the total income, and the number of rooms in a house, and we want to predict the average price of the house, Then we can, for example, calculate the Shapley value of the number of rooms, let's say 6 in an example house. So let's say we have 6 rooms in this house and we want to know what that means for the final prediction of the house value. Then we're going to add this value to different coalitions, namely the one in which we only know the number of occupants, the total income, the coalition in which we know both, and the empty set. So we are going to sample everything. And for each 4 coalitions, we're going to do this. For example, for the number of occupants, we're going to take the number of occupants, which is the upper row, the middle row actually, from the instance we want to have explained. So let's say that's 2. And we're going to sample the income, because the income is all the other variables, because there are just 3 variables in this example. And we're going to put our number 6 for the number of rooms. And in this case, the prediction is, for example, 300,000. Then we're going to do something else. We're going to almost do the same, but the only thing we're going to change is that the number of rooms we're going to sample randomly from the training set as well. And then we can sample as many times as we want to. We can try as many coalitions as we want to. This, of course, becomes very expensive. If you have like 100 variables, you will get 2 to the power of 99 coalitions you have to try. So that's infeasible. But we get one nice number to quantify the contribution of a variable to the prediction. So if you recall, latitude was between -0.5 and -1.5 in the breakdown plot in my 50 samples, and now it has one value, which is about minus 87, minus 0.87, I mean. And this is also very easily to implement in DALEG. The main thing you have to change is for the predict parts, you can use the same explainer, but for predict parts, you have to give in the type being SHEP instead of breakdown, and you don't need to specify the order because this is the order doesn't matter for Shapley values. So that is a big plus for Shapley values, I think. You just get one single value which can quantify the contribution of that variable to the prediction. It has a strong foundation, and in game theory is mathematically really sound but also expensive if you want to do it correctly. But sampling often is good enough. And it works very well for additive contributions. On the other hand, it does not show interaction effects because we are going to add every variable to all possible coalitions, but we're not going to add groups of variables to the coalitions. So this really does not show these effects. And another drawback is that it's very time consuming if we have large data sets. Okay, so for my last explainability method I'm going to explain today, that is Lyme. This is also a very well-known and widely used method. It stands for local interpretable model agnostic explanations. And what we're going to do is basically we're going to fit a simple model around as a wrapper around the predictions of a black box model. And with that, we try to explain the behavior of the black box model. Well, I would say it's a good thing and a bad thing that it's an oversimplification. Mostly we just want a simple answer because that is understandable for most people. But it also it's not really precise sometimes. So we're going to permute the data first because we want data to make predictions on. So our point of interest we want to explain is 80-60, x60y. And all the other points are just randomly sample generated points. Then we're going to calculate the distance measure for every point to that point. So every point has some distance measure. It's totally up to you how to choose it. Actually, it's also totally up to you how to choose how to permute your data. Then we're going to make predictions with the black box model. So for example, this black box model could make these predictions. The dots in the middle are classified as black, and the dots on the edge are classified as white. Then we're going to choose the features we want to have explained. So for the sake of this example, I only took 2 because that's better visualizable than 3 or more. But of course, you can have 100 features of 100 variables. Then you can choose some you can use with the principal components or whatever you want to. But the important thing is that we're going to choose features. We're not going to use all of it because then there will be no use in using this method. And then we're going to fit a simple model, which you can choose which kind of model this is. This can be a decision tree or a regression model, a model that is interpretable and understandable. So this fitting of the simple model is done based on the distance measure. So all points that are close to the point of interest are used in this the fitting of this model. We could, for example, say that we are only going to use the points to train our model that lie within this red circle. And if we do this, we will probably get a model that predicts the points in this way. So just one vertical line at 80x. So now we get the explanation on the right side. That's the model we have trained to explain the model, the behavior of the model on the left. So we can see that this is not accurate at all. But it makes sense in a way, because if I would ask you why is this point classified as white, you would think it is because it is it is to the right, enough to the right to be classified as white. And that is basically what the model on the right says. Of course, if it were very much to the left, it would have been white and not black. But this is an intuitive explanation on why this point is classified as white. This is also, we're also able to do this in Python as well, of course, with a Lyme library. So it is quite similar to the Dalek library in terms of how we're going to use this. So first we're going to create an explainer object with a training set, and we want a regression model, and we're going to use the feature names. For this example, I use train column, so all the variables. But of course, if you have many variables, you will make a selection here. And then we can use, with the method explain instance, we can get an explanation or actually we can train a simple model that serves as an explanation for this black box model. And the cool thing about Lyme is that it also works for images, so this is a detector of snow, actually. It should be a detector of wolves and huskies, okay. So let's start. So we can describe an image as a collection of superpixels, so parts of an image, and we can either turn them on or off. So the original image would be like 100 variables indicating every spot of the image all being one, because it is all shown. And then we can make permutations on that as well, which means that we leave some parts out, and we do not present that to the model, and then we ask the model to make predictions. Then what it does, then we can train a simple model in the same way as we did with the tabular data, and then we can identify the most important variables, so the most important bits, parts of the image for the class wolf or for the class husky, and that is what's being shown here. So on the left, you can see wherever wolf is predicted, the most important pixels contain just snow, and even though the accuracy is quite high on this model, we can see that it probably does not want what we want it to do. The same holds for text. So we can also use Lyme for text, because we can also code text in a way that every word is a variable and is either turned on or turned off. So we can permute this data set or this sentence in a way as we can create new sentences. For example, movie was not bad at all, this was not bad at all, this, etc. And then we can do the same as we did before with the tabular data and the images. And what's shown here is the coefficients of the simple model for each word, so for each variable being set to a word. So no, turned on or turned off. So if the word bad is turned on, then it most likely, most of the times, it's given a negative sentiment, or a negative sentiment is predicted. So what we learn from this is that this model does not really handle the combination of not and bad very well, because this sentence does not really have a very negative sentiment, but the model thinks it has. This is, of course, a simple example. We could also find this out in other ways, but this really lets you see what the model picks up on. So the pros and cons of Lyme are that I think it's very readable and very visual, especially for images. We can really see what parts of the images a model focuses on. Of course, there are also other ways to do this, but I think it's great that Lyme is also applicable for different kinds of data. The drawbacks of this method is that the definition of the neighborhood is very hard. So, for example, the red circle I draw to include the points for which I'm going to fit my simple model on. You can make it bigger, you can make it smaller, you can make it differently shaped, and that will really influence the prediction of the simple model, or actually how our simple model looks like at all. So sometimes explanations are a bit unstable, especially if you have more variables. So your decision space will be a bit more not so straightforward as the image I showed with 2 variables. So sometimes it's hard to be sure that is the right explanation, that is the explanation you want. So to summarize, I think there are many reasons to explain your models. I think performance is very important, of course, but explanation in some cases is better. There are also many ways to explain your models. I just described 3 ways of explaining your models. These are all model agnostic local explanations. So there are 3 other categories of models which I haven't touched at all. The ones I explained were breakdown plots, Shapley values, and Lyme. Another thing I want to mention is that the Dalig packages, so I use the Dalig package for this, and the Lyme package. The Dalig package is great to look at. It really has a lot to offer. The Lyme package as well. So here I've written my email. If you have questions, feel free to email me. And the GitHub we developed with Rig, so that's also given. So there is an Explain AI workshop, so that explains a lot of techniques, also different techniques from the ones I've explained today. So if you are interested, take a look there as well. Okay, thank you.